Okay, we're going to go ahead and work on section 2.3 now, and this is solving linear equations. So this is pretty much just picking up where we left off on the very last part of section 2.2. We're just going to be using the addition and the multiplication properties of solving equality in this section exclusively. Again, this is very similar to what there was a table in section 2.2 that it might be good to print out. This is the same thing, just step by step for solving equations. Simplify the expression on each side, collect the variables on one side and constant terms on the other, isolate the variable, that means to get a 1 in front of it, and check the proposed solution by plugging in the value you get into your original equation. We're going to go ahead and work on solving. We're not going to be checking yet, but you can go ahead and check on your... Oh, it does say solve and check, so we will solve and check. So they give us an equation, 7x is equal to 3 times the quantity of x plus 8. So the first thing we want to do is we want to use distributive property. We distribute 3 to everything inside. 7x is equal to 3x plus 24. We distribute 3. Next, we know we want to get the variables on the left, constants on the right. Well, we need to get rid of the variable on the right by subtracting 3 from both sides, and we end up with 4x equal to 24. We know we get rid of the 4 by dividing by 4 on both sides. 4 divided by 4 is 1. 4x divided by 4 is 1x. 24 divided by 4 is 6. So now we have x is equal to 6. We've solved our solution. The one thing we want to do now is we're going to want to check our work. So we get this solution and we plug it into our original equation. So everywhere we see an x, we put 6. So 7x, 7 times 6 is equal to 3 times the quantity of 6 plus 8. And we know that from order of operations, we do multiplication first, or actually parentheses first. So that whatever's in here, 6 plus 8 is equal to 14. And now we have 7 times 6, which is 42, is equal to 3 times 14. 3 times 14 is 42, and we had 42 on the left, so 42 is equal to 42. That means this is a true statement. That means this is a correct solution. Here they give us a word problem. The formula P is equal to 15 plus 5D divided by 11 describes the pressure of seawater in pounds per square foot at a depth of D below the surface. At what depth is a pressure 30 pounds per square foot? Substitute the given pressure into the equation for P. P is equal to 30, so the same pressure is equal to 30. They want us to find how deep we are. The equation becomes 30 is equal, because we just substitute 30 everywhere we see a P. 30 is equal to 15 plus 5D over 11. And now we have to solve that. We have to find our depth. The way we find our depth is we've got to work through all these little steps to get the D all by itself. So one of the first things we can do, and one of the first things we can do, I would have done this a little bit differently than the book did, but it looks like they multiplied by 11 on everything. So if you multiply by 11 on this entire solution, on the right, you can multiply by 11 on everything on the left, and you get 30 times 11 is 330. You got to distribute the 11 to everything inside here, makes it 165, plus the 11 cancels with 11 there, and we get 5D. Now we go ahead and bring our constant terms from the right to the left, and we get we subtract it. We see we have to subtract 165 from both sides, and we get 165 is equal to 5D. Now we got to get the D. We got to isolate the D. We isolate the D by dividing by 5 on both sides. So 5D divided by 5 is equal to 1, or D, and 165 divided by 5 is equal to 33. So now we have the solution. D is equal to 33 feet. Again, here's the tips again. Very, very important to learn. Take this as a hint that we're showing it many times. That means it's really important, so probably a good thing to print out and keep handy. Now we're going to look at something where everything's a fraction. I know fractions really scare people, but they're no different than working with real numbers, with regular numbers. That they're just, remember, fractions are just numbers. So when we simplify algebraic expressions on each side, the first step we want to do, sometimes it's really helpful, is to find the least common denominator of all of your fractions. So we see 3 and 5 and 2 are our common denominators. We need to find the least common. 3 and 5, the lowest is going to be 15. but 2 is not a 2 doesn't mix with the 15, so we go one more up, and that's going to be 30. So we find out our common denominator is going to be 30. We'll multiply everything by 30. So 30 times this term minus 30 times this term is equal to 30 times this term. And we simplify that out. We get 10 because the 3 and the 30 cancel. We get a 1, and that turns to a 10. This goes to a 6. This goes to a 1. This goes to a 15. This goes to a 1. And now we have this. They keep the 1s there just to make it a little cleaner. And then now they just get rid of the 1s here. We get 10 times 2x minus 1 minus 6x minus 2 is equal to 15x. Now you see, this is all still the same exact equation. It just looks different. We can do anything we want to these equations as long as we do it to both sides equally. Okay, that's the main rule here. So now we have a solution, equation that we're used to seeing. We know how to handle this one hopefully by now. We go ahead and use distributive property. Next we combine like terms and we get 14x plus 2 is equal to 15x. Then we get the variables on one side and the constants on the other. In this case we're going to move the variable 14x to this side. Since it's easy, since we don't have any constants to move to this side, we'll move the variables out of there and get a constant by itself. And we end up with 2 is equal to x. So isolate the variable and solve. Well, it's already done whenever we move things over. It worked out real nice for us. So we've had the solution x is equal to 2. Now we've got to check this solution by plugging a 2 everywhere we see an x. So we get 2 there, 2 there, 2 there. And we work down. We just use order of operations to work down, so I'm not going to go step by step because we should know order of operations by now. And when we get to the end solution, 1 is equal to 1. So this is a true statement since 1 is equal to 1. And we can say this is indeed a solution of the original equation. Now, sometimes you're gonna see some instances where linear equations have no solutions, and when we try to solve for our variable x, we're gonna get something weird. And here's a good example. Here we have 2x is equal to 2 times x plus 3. We go ahead and use the distributive property. We get this. Then we move the variables from one side to the other. So we subtract 2x from both sides. And when we subtract 2x from the right, we get 0x. When we subtract 2x from the left side, we get 0. So now we have 0 is equal to 6. That is a false statement. That is never true, right? 0 is not equal to 6. So we stop there and we say, okay, this is incorrect. We can't simplify anymore. We can't solve it. This is false, so it is no solution or inconsistent. Okay, no solution. And there's also cases where we have a linear equation that have many solutions. And here's an example of that. I'll show you what that looks like. So we have we'll go ahead and solve this guy. Use the distributive property. Bring all the variables to the left, all the constants to the right. When we end up, we get x, or 10 is equal to 10. There's no variable here, so we don't have an answer for x. What this tells us is any number you put in here will make this problem equal. Okay, so every number is a solution, not just one particular one, but every problem. So anytime you get something like this at the very end, that means every number is a solution. And we could have noticed up here later on. We'll notice that we could have stopped up here. We could have stopped up here and said, "Yep, 5x plus 10 is equal to 5x plus 10." Oh, we don't have to go any further because they're exactly the same. Categorizing an equation, an identity. So yeah, we do call it an identity where every real number is a solution to the problem. A conditional is what we normally find, and inconsistent is when the statement is not true. So I'm going to take a quick break. So we're running out of time, and come back and finish off the last few slides and do some examples.